needs any introduction, at least to Indian mathematical community. So it is my pleasure to introduce, nevertheless, it is my pleasure to introduce today's speaker, Pritam Ganguly, and he shall be talking in norms on Harish-Chandra module. And with this, I would like to invite him to deliver his talk. And I also request all the participants to mute their at least microphones. Okay, so over to you, Pritam.
Okay, so thank you, Munada, for the introduction and the invitation to speak today. So as the title shows, I will talk about norms on Harish-Chandra modules. This is based on a joint work with Bernstein, Bernard Krotz, Yopkout, and Ethan Sayag. So let me start with some notations and a bit of motivation. So throughout the talk today, G will be a real reductive group, and the corresponding Gothic Fraktur notations will denote the Lie algebra, and K is a maximal compact subgroup. So for example, you can always think about G to be SL2R and K is SO2. And in this talk, by a G representation, we always mean a topological vector space for which is equipped with a continuous G action, that is a group homomorphism, such that this action map is continuous. And whenever there is no confusion, so we can drop pi from the notation and simply write G dot V. And there are two relevant subspaces of G representation for us. One is the smooth vectors, which are all those vectors in E for which the orbit map is a smooth function. And another subspace is the K finite vector. So this is this should be E, not V. So all those vectors in E for which V lie in a finite dimensional space spanned by the K action. Okay, now coming back to the title of the talk, Harish-Chandra module. So what is Harish-Chandra module and why do we care? So to answer this question, let me just begin with the basic question of representation theory. So one of the main goal of representation theory is to understand groups through their actions. It's like in real life. If you want to understand a person, you have to understand his or her actions. So the goal is to sort of classify all sort of possible actions or how the group acts on different spaces. So typically, we want to realize representations or actions of a group on a space of functions. For example, if a group acts on a set X, then it naturally acts on the set of all functions on X. But the main difficulty is to decide which space of functions to consider. For example, if X is a smooth manifold, then you can consider smooth functions or continuous functions on X. Or if your X has a nice measure attached to it, then you can also consider different LP spaces. So let us try to understand this situation or understand the issues here by looking at an example. So let's take the example of SU11, which is all those 2 by 2 complex matrices having determinant 1 of this form. And this is actually an isomorphic copy of SL2R. So SU11 acts on the circle by fractional linear transformation. This is basic complex analysis. And this gives rise to representations of this group in different function spaces like continuous functions or smooth functions or L2 or the distribution functions on the circle. And the action is same in all this case. So the interesting thing is that although these representations, they look same algebraically speaking, but the spaces on which they act, they are topologically very different. So naturally, to have a reasonable classification, it is desirable to identify them in some sense. Now here comes the master with his idea of infinitesimal equivalence and resolve this issue. Harish-Chandra first identified that all these spaces shares a common algebraic skeleton, which is basically in this case is basically the functions on the circle with finite Fourier expansion or the trigonometric polynomials. And this actually turned out exactly to be the K finite vector in this case. And also it turns out that this K finite vectors is actually not closed under the action of the group. However, it is certainly closed under the action of the both Lie algebra and K. And this leads to the concept of infinitesimal equivalence. Let me just roughly present you the idea of Harish-Chandra. So you have to start with admissible representations, let's say pi e. So admissibility basically means so you can screen your representation over the action of K. So you get a algebraic direct sum of the K isotypic components. And admissibility basically means the dimension of this isotypic component is finite, and finiteness of this dimension will tell you that the K finite vectors will all be smooth vectors. And once it is a smooth vector, then your Lie algebra naturally acts on them. And you already have a K action. So these give rise to what is called a GK module. And interesting thing is, there is a bijection or one-to-one correspondence between the closed G invariant subspace of the representation with the GK submodules of these K finite vectors. All this basically tells you, okay, if the representation is irreducible, if and only if is the corresponding GK module is irreducible. So this way, Harish-Chandra reduces the classification of representation to classifying all these GK module. That's why now you don't have to care about this topological object. Now everything boils down to classifying this algebraic object, where you can use different algebraic methods.
Pritam, there
Yeah.
is small basic question. E infinity probably is EK finite, okay? It is completely, or this subset is proper?
So since you have an admissible representation and your isotypic components, that means the dimension of the isotypic components are finite, your EK finite will be contained in the smooth vectors. All the K finite vectors will be smooth in this case.
No, I am saying this containment is really strict or not strict? This
This is strict.
Not this is strict. Yeah. So
Yeah.
this is not this near. Okay.
Yeah. Both are dense subspaces, but yeah.
I understand.
There
This is
could be
not
smooth functions. For example, you look at the circle, you can have smooth functions still. For example, you take any analytic function on the circle, it may not have finite Fourier series.
Yes.
It may have infinite Fourier series. Right?
Yes.
Okay, so for admissible representations, Harish-Chandra proved that any irreducible unitary representations are admissible representation, and the concept of infinitesimal equivalence basically says that the algebraic equivalence of these K finite vectors. So that's how GK module comes into the picture. Now, if you want to classify representations, you just go to this. Classifying representation will be hard because of this. It may involve some topological complications. Then using this Harish-Chandra's technology, you just go to the algebraic object. Now use algebraic tools to classify all those GK modules. Then you go back. That's the idea of Harish-Chandra. Now, okay, let me just formally define all these objects. So what's the GK module? It's a algebraic object. Basically, there is no topology involved. It's a vector space with a G and a K action both. G means here the Lie algebra G, and such that the derived action of the group K should coincide with the action of the Lie algebra when restricted to the Lie algebra of K. And these two actions must be compatible in this sense. Well, now a GK module is called a Harish-Chandra module if he is admissible. That is, for every irreducible unitary representation of K, the Helm space is finite. So basically, this means the every irreducible representation appears with finite multiplicity, and V needs to be finitely generated as a UG module. UG is the universal enveloping algebra, and this is a purely vector algebraic object, which is a vector space of countable dimension because of this admissibility. And well, Harish-Chandra also proved that if you start with a irreducible unitary representation, then the K finite vectors are.
What did you say about this countable dimension thing?
Okay, so if you look at UG.
Okay.
UG is the countable direct sum of these powers of your Lie algebra, right? So this is a countable dimension thing. And finitely generated means there will be a finite dimensional K vector space for which if UG acts on that vector space, it will give you the full. That means it can have at most countable dimension.
Yes. Okay.
So throughout the talk, given an irreducible unitary representation by the k finite vector, we will denote the corresponding Harish-Chandra module. Now, whenever you have a Harish-Chandra module, which is purely an algebraic object, now the question is whether does it necessarily comes from a representation. That means whether there is always a representation for which the k finite vector is actually isomorphic in some sense with this Harish-Chandra module. So this the globalization questions. So the definition is given a Harish-Chandra module. We'll say that a complete locally convex topological vector space is a globalization of V if E supports G representation, that is E is equipped with a G action such that the k finite vectors are isomorphic, GK isomorphic to this Harish-Chandra module V. Okay. Now these globalizations are far from being unique. For example, if you take X to be a compact homogeneous space of G, for instance, you can take X to be G by P, where P is a minimal parabolic, and you look at V to be all those k finite vectors in this L2 space intersected with the smooth vectors with respect to the right regular action of G on L2, then this turns out to be a Harish-Chandra module. And for this Harish-Chandra module, L2 space serves as a Hilbert's globalization. And also, if you look at, instead of L2, if you look at the analytic functions on X or the smooth functions on X, they also turns out to be globalizations with their respective topology. For example, this is the analytic globalization or smooth globalization. Another example, another interesting example is by Schmid, who proved that, okay, there is something called a minimal globalization of a Harish-Chandra module, and which actually coincides with the analytic vectors. So this minimal globalization, for instance, is a globalization which is an inductive limit of Banach space. There is no particular norm. Now, whenever you have a vector space, there could be a lot of norms on it. So for example, let me just fix a notation. If V is a Harish-Chandra module and P is a norm, then we'll call VP the completion of this norm space. That's VP is a Banach space. So in Harish-Chandra module, there could be a lot of interesting or lot of norms. Now, the norms that we are interested in are called the G continuous.
Can you go back to the previous slide?
Yes.
So the thing is, you are saying this B minimum. This is not definitely not a Banach space, right? It is a
No, this is not a Banach space. This is inductive limit of Banach spaces. So there is no norm on it.
But it may happen that given this Harish-Chandra module, you can get a Banach space, which is the globalization of that.
Exactly, I'm coming to that.
Okay.
That's why I said, given a Harish-Chandra module, the globalization is not unique. There could be different globalization. For example, if you look at this example, there is Hilbert globalization, there is analytic globalization, then there is smooth globalization. So all these globalization.
Why this is called minimal globalization?
So in some sense, this sits inside all the globalization.
Okay. Okay.
So I'm not going into the details.
You cannot explain at the end if you have. Okay.
That means you cannot get any globalization which is below this.
Okay.
Okay, now coming back to the thing that we are interested in, norms on Harish-Chandra module. So what kind of norms we'll be looking at? We'll be looking at this class of norms which are called G-continuous norm. This term is coined by Bernstein and Krotz. So a norm on a Harish-Chandra module is called a G-continuous norm, provided the completion VP supports a G representation such that this K finite vectors is isomorphic to V. GK isomorphic to V. So for example, so basically this G continuous norms gives you this Banach globalization. Okay. Now, why does such norm exist at all? For this, we'll thanks to the Casselman subrepresentation theorem, which says that if you start with any Harish-Chandra module, you can embed this Harish-Chandra module inside the Harish-Chandra module of the induced representation induced from the minimal principal series. And then this induced representation, since being a subspace of some LP function, so some function spaces, sigma valued function spaces, can think of on a function space, the same norm can be given on the Harish-Chandra module. So, for example, those spaces also have some G-continuous norms. For example, you take the L2 norm, which is a G-continuous norm. Okay. Now, with the Harish-Chandra,
Pritam, how do
yes.
you conclude? Could you explain the third point? I think your voice also was shattered. So.
Okay, so V is embedded. This is from the Casselman subrepresentation theorem that V is embedded in a Harish-Chandra, I mean the k-finite vector of the induced representation, which is induced from the minimal parabolic. So this is already a representation. So you already have a G-continuous norm here,
Okay.
which is the L2 norm, L2 of G mod P. It's basically k by k. If you use the Iwasawa decomposition, then and P is MAN, then you can see this is basically k by k intersection P.
Okay.
So the point is to show that on Harish-Chandra module, you can give any norms in any norm which you have on the function space. And out of those norms, we are interested in the G-continuous norm, which supports a G representation for which it captures the Harish-Chandra module.
I think you are assuming the irreducibility of B also, or some condition to apply this Casselman subrepresentation theorem. Some kind of.
No, I think this is true for any Harish-Chandra module.
Any Harish-Chandra module? Okay. Okay. It may be.
Yeah, it doesn't really matter. It's just to show that there exists G-continuous norm. Okay. Now with the Harish-Chandra.
Yeah.
Sorry?
No, I think it may matter actually. If B is not irreducible, then or something like that, so then probably it may problematic. I think so. I don't know. Okay.
So I think the Casselman subrepresentation theory is for any Harish-Chandra module.
Any Harish-Chandra? Okay, that
yeah.
Probably. Okay.
Okay, so with the Harish-Chandra module, there is something called a dual Harish-Chandra module. So Harish-Chandra module is a algebraic object. So you look at the algebraic dual, that basically means all the linear functional, and you look at the k-finite vectors in this. So this will also turns out to be a Harish-Chandra module. That is, it satisfies this admissibility and the finitely generated condition over this universal enveloping algebra. And it turns out that all these Harish-Chandra modules are reflexive. That is, you take dual to the dual, it comes back to the previous one. And given a G-continuous norm on a Harish-Chandra module, we can define a dual norm by simply using this dual formulation. And this also turns out to be G-continuous. That is, if you have a G-continuous norm on a Harish-Chandra module, you also have the corresponding dual norm is also turns out to be a G-continuous on the dual Harish-Chandra module. And this dual norm has certain properties which are important for us. If, for example, if PQ are two G-continuous norm on V, then so if you dualize the dual norm, you come back to the original norm. And if P is dominated by another norm Q, then for the dual norm, the inequality reverts. Okay, now comes back to matrix coefficient corresponding to a Harish-Chandra module. So we first fix a G-continuous norm and VP being the completion. So, and the action of G on the VP, I call it pi P. And there is a canonical identification of this dual Harish-Chandra module with the k-finite vectors of the strong dual of this VP. Then you take V from V and then VP tilde from this dual Harish-Chandra module. And then it turns out that this map, that VP tilde of pi PG of V is an analytic map. And this analyticity or this map is actually independent of the choice of P. This
Sorry,
is
I couldn't
roughly
follow it quickly. Can you really? So the thing is, B tilde is the dual of B, right? And what
yes.
is BP prime K finite?
So V tilde is a dual of V, but if you have a G-continuous norm on V, then you have a completion VP, right?
Yeah.
Now, VP prime is the strong dual, that is continuous linear functionals on VP. So you have now a topology, you have to consider that. And if you inside that, if you look at the k-finite vectors, then there is a canonical identification with the usual dual and this dual. Just simply V goes to VP tilde. V tilde
You
goes to
mean,
VP tilde.
you mean if you take the algebraic dual of V, that can be identified with topological dual, but only k-finite vectors. This is what you're saying.
Identified with the topological dual if your original Harish-Chandra module has a G continuous norm.
Okay, thanks.
Otherwise, it's not true. And this basically says this function that G going to this thing is actually analytic, and this is independent of the choice of this norm. You choose any completion, doesn't matter, any G continuous norm, this function stays the same. And this is roughly because analytic functions are determined by the derivatives. So this is observed in this paper of Casselman. So henceforth, we just call matrix coefficients attached to V and V tilde as this. We can drop the notation P because this is actually independent of the choice. Okay. Now there is something called growth of a representation, which is often modeled by weights. So weights are basically locally bounded positive functions, which is submultiplicative. That is this. So for example, if you have a G continuous norm, so every G continuous norm is bounded by a natural weight, which is this operator norm. And given a Harish-Chandra module and a weight W, we consider this space norm VW, which is basically all those G continuous norm for which the growth is bounded by the W, this weight W. So this basically our overall aim is to structure this set, to understand this set better geometrically. This set actually corresponds to the Banach globalizations of Harish-Chandra modules with fixed growth rate. And for example, if W is 1, this corresponds to the G invariant norms, that is the isometric norms. And in this case, which will drop the notation W, drop W from the notation. So these are all G invariant norms, which is of course the most interesting ones. Okay. So let me start with some examples example of norm in this norm VW. The first one is the tempered representation. So let's start with a semi-simple Lie group with finite center. Take a unitary irreducible representation, which is tempered. So tempered basically means it appears in the Plancherel decomposition of L2. And take V to be the corresponding Harish-Chandra module, that is the k-finite vector of this representation. Since it's unitary, you can fix a unitary norm on V. Now recall that if phi is tempered, then all the k-finite matrix coefficients should lie in L2 plus epsilon, that is LR such that R bigger than 2. Then this gives rise to certain isometric norms. So you can fix V tilde from V tilde, the dual of the Harish-Chandra module, and you define this matrix coefficient and take the LR norm. This turns out to be isometric norms, and these are all G invariant G continuous norm. That is, if you take the completion, this will support a representation for which this the k-finite vectors will be isomorphic to this Harish-Chandra module. And this
one question,
choice of it, yeah.
It's an isometric norm for any V tilde.
Yes, because it's irreducible. Actually, you can take the cyclic one.
Let's see.
Yeah.
Okay. Yeah, go ahead.
Okay. Now, in our setting, we have an interesting formulation of the Kunz-Stein phenomena, which says this all this isometric norm, this LR norm, sits below the unitary norm. So this is an equivalent formulation of this Kunz-Stein phenomena. Kunz-Stein phenomena. Let me remark that.
Pritam, what did you answer to the Naru's question? That V tilde is cyclic.
Yeah, so it's a irreducible. It comes from a irreducible representation. So all these V tilde and V are irreducible. So you can get a cyclic vector inside.
So you have to take this V tilde cyclic, or what?
Yes.
It's irreducible, so any vector will be
irreducible.
cyclic.
So any vector will be cyclic. So that's why it is fine.
Okay, carry on.
And in our setting, Kunz-Stein phenomena looks like this is actually an equivalent formulation of Kunz-Stein phenomena. which is proved by Cowling in full. Now, another interesting example is the automorphic norms, which goes back to Bernstein and Reznikov. So you start with SL2R and take gamma to be a co-compact lattice. That's a discrete subgroup of SL2R such that this quotient is compact. And let's take E to be a k-spherical unitary principal series representation. Then look at the k-finite vector, that is V to be the Harish-Chandra module. And suppose this is automorphic, that is there exists a continuous gamma invariant functionals on the smooth vectors. And we consider the automorphic form because this is simply the matrix coefficient with respect to this eta and NEV. And this turns out that Q given by this L2 norm of this matrix coefficient is a unitary norm. It coincides with the unitary norm. And there is another interesting norm is this L infinity norm of this matrix coefficient. This is also turns out to be isometric norm, and which we'll call the automorphic norm. This actually, this automorphic, this L infinity norm has some importance from this automorphic point of view. I'm not going into that. Actually, the rigidity of these lattices are actually encoded inside this L infinity norm. That's why we are calling it, we are taking only this. Otherwise, you can take any LR norm if you want. And it turns out that, okay, since X is compact here, so Q is always dominated by some volume, square root of the volume times the automorphic norm. And as shown by Bernstein and Reznikov, this automorphic norm always sits below the Sobolev norm, fractional Sobolev norm associated to this unitary norm. So I'll come back to the definition of fractional Sobolev norm in a moment. Whenever S is bigger than 1/2. So this is actually, if you can view, it is actually like a Sobolev embedding theorem, but which is better than the Sobolev embedding theorem because you only need half here. Okay, so we have shown some examples. Now coming back to our problem, we want to structure this set norm VW. So on this norm VW, there is a natural equivalence class, equivalence relation. That is, we say that two norms P and Q, two G-continuous norm P and Q are equivalent if and only if P is eventually dominated by Q and Q is eventually dominated by Q. So this notation means P is less than equals to some constant multiple of Q. And this equivalence class, this equivalence relation leads to this equivalence classes of norms, which we usually denote by this notation. And note that this less similar equal to sign on norm VW induces a partial order on this equivalence classes of norm. And then we have our first proposition, which says that if norm VW is non-empty, then this norm VW, this equivalence classes of norm, actually features a unique minimal and a maximal element. So let me give you a idea of the proof of this in a special case. So let me assume that V tilde has a cyclic vector.
So, just a question.
Yeah.
You are not assuming anything on the weight yet.
No, not.
No.
I'm not assuming.
But is
anything.
there any condition on the weight which implies norm VW is non-empty? And W1 will work probably, but
yeah, for example, if you have so far we don't really have any condition on W that will certainly imply that this is going to be non-empty. We'll only consider those W for which this is non-empty.
Yeah, okay, go ahead. Yeah.
And so one is the example that I already showed. You start
Yes.
with any G-continuous norm, you have already that operator norm WP.
Yes.
You always have examples of W for which this is non-empty.
Okay, yeah, got it.
Yeah. So I'll give you the construction, and so not only the existence of unique minimal and maximal elements, we actually have formulas for this. So I'll give you a construction of this minimal and maximal norms in a special case where V tilde as a cyclic vector. So for this, a representative for the equivalence class of minimal norm would be you take the matrix coefficient associated to V and V tilde, divide it by the weight and take the supremum. Okay, now the few questions arises. Why does it exist at the first place? Why is it a norm and why is it G continuous and all these things? So let me answer this one by one. So if you start with any G continuous norm, since it's non-empty, you can take any. That means P G dot V will be dominated by some constant multiple of weight times the norm. Now come back to the matrix coefficient. This is simply the coefficient, the norm property of norms, the continuity. Then using the above, you can also dominate the second line by this, second thing by this, the WG, PV, P tilde. Then simply calling this C times P tilde as C tilde as a constant, since the V tilde is fixed. We see that V min, P min is basically less than equals to C tilde times P. So that basically shows this is a finite, the supremum is finite, so it's a norm and it sits below any norm you take. So it's a minimal norm. And why it belongs to that norm VW class? So that follows from the submultiplicativity property. So we use the submultiplicativity of the weight to show that if you translate by G, translate a vector by G and take the minimal norm, then it becomes this. And then you just take a change of variable in the supremum, then this W comes out. So this shows that this is actually in norm VW. And now why it is G continuous? This simply because if you start with any G continuous norm, it actually, that norm dominates this minimal norm. So because P is G continuous, then that will imply that odd bit maps corresponding to this minimal norm is continuous for V. So this is a representative for the minimal norm. We actually have a formula. Now for the maximal norm, you just dualize this construction. That means you go to the dual of the Harish-Chandra module. You look at now we fix a cyclic vector in the main Harish-Chandra module. You look at the minimal norm in the dual module, then come back. Then the dual of the minimal norm will turn out to be a maximal norm here because of this relation in the beginning that I presented. Okay, so you have so in fact, if V tilde doesn't have any cyclic vector, we can just take another supremum where the supremum we should take over the generators. So it will have finitely many generators because it's a finitely generated module. Okay, now let us start with some Sobolev norms on a Harish-Chandra module. So we fix a norm P.
So there is a, you said that there is also an expression for this maximal norm. Or what is that expression? It is
expression means I meant just you go to the dual Harish-Chandra module, you construct the minimal norm there using this prescription. Then you dualize that.
Okay. So whatever that will be maximum.
Yeah, that is going to be the maximal norm.
Oh, okay. Because of that, yeah.
Yeah. So now we have Sobolev norms on a Harish-Chandra module. So given any norm, you fix a norm P on a Harish-Chandra module and fix the basis of the Lie algebra. Then for every K, this expression defines the standard Sobolev norm of order K. So you take derivatives up to order K. And in fact, I am saying a Sobolev norm because different choice of basis leads to different norm, but all those norms are equivalent. And one of the major advantage of this definition is that this norms becomes monotonic. Also, if you fix a priori, if you fix a G continuous norm from norm VW, then this Sobolev norms also turns out to be G continuous, but they may not belong to the same class because in that case you have to enlarge the weight. Now comes the globalization theorem of Casselman-Wallach. So there are a lot of formulations. Actually, the original by Casselman or the Wallach, which is more algebraic one. but I always prefer this analytic one. It says if you have any pair of G continuous norm PQ on a Harish-Chandra module, then they are Sobolev equivalent in the sense that there exists a K such that P is dominated by the standard Sobolev norm of Q of order K and vice versa. So this basically says that if you have any two G continuous norm on a Harish-Chandra module, these families of Sobolev norm corresponding to those two norms define the same topology on that Harish-Chandra module. And this means the identity map, whatever is there from V to V, this actually extends to a G isomorphism of H spaces of the smooth vectors of when you consider with P or you consider with Q. So that basically says the smooth globalization is always unique. And this globalization will denote it by V infinity. So it doesn't matter what norm you choose, what G continuous norm you choose, the smooth vectors will always be same. So that's the power of this theorem. Okay, now another interesting thing to consider other Sobolev norm is that, so if you start with any G continuous norm on a Harish-Chandra module, a vector V in the completion VP is smooth if and only if it is K smooth. This is also observed in this paper. So this basically says to check the smoothness, it is enough to check the K action only. And this leads to another definition of Sobolev norm, which we'll define now. So we take V is a Harish-Chandra module, P G continuous norm. Now you take the Laplace element from the universal enveloping algebra corresponding to the group K. So this is basically sum of squares of the basis elements from the Lie algebra K. And you look at ds to be the fractional power of 1 plus delta K. So this operator acts on the K types as a scalar. And then we define the S-set Sobolev norm, which is S is for any R to be the P applied to ds times V, ds applied to V. So for example, if you take G to be SL2R, K is SO2, then K hat here is identified with Z. So you can expand any vector in K types. So PSV will be exactly 1 plus mod to the power S times Vn. It's like the Sobolev norm on the circle. Okay, so with these definitions in hand, now we define, okay, some more thing. So if P is a G continuous norm, then you look at the Sobolev norm, which is denoted by ASS. So there are some properties of this Sobolev norm, that is, it respects the inequality, that is if P sits below Q, then the corresponding this Sobolev norm will also be dominated by the other Sobolev norm, and it has this semigroup property, which is all these things are easy to verify from this object ds. And most importantly, it has the duality, that the dual of PS is actually P minus S. But there are some issues. The first issue is PS may not be a G continuous norm. But this issue is again a minor issue because PS always squeeze between two standard Sobolev norm which are G continuous. And PS is certainly not monotonous. For example, if S is bigger or equals to 0, P is not less than equals to PS in general. But if P is K Hermitian, this is certainly is. For example, if you take unitary norm, this is certainly monotonous. Okay, now we define our, so with this definition of Sobolev norm in our hand, we define a distance on the set of all G continuous norm, whose growth is bounded by W. You take PQ, two equivalence classes of norm, and you define the left distance to be infimum of all those S, for which P is eventually dominated by the Sobolev norm corresponding to Q. And you take the infimum over this Sobolev degree. That's what you call the left distance. And to make it actually a distance, that is to make it symmetric, we take maximum of these two. And this actually turns out to be a pseudometric. That is, it has a triangle inequality, symmetry, but there are norms for which the norms are not equal,
just
but the distance may be equal. Distance may be
question,
0. Yeah.
Pritam.
Yeah.
So the Q sub s was defined using K, right?
Yes, K.
Okay.
So yeah, so Q sub s is defined using K. So
Okay.
the dependence of this norm over K is
But you don't know
not.
if it is G continuous.
Yeah, exactly. We actually don't know it is G continuous, but there is a remedy for this. I will come back to it.
Yeah.
But just for the time being, this is the definition of the distance.
Okay. Okay. Go ahead. Yeah. Yeah.
But
Yeah,
then you
we
said
don't need.
QS. Okay, go on. Pritam. Go
US
on,
is
please.
squeezed between two G continuous
Yeah.
norm, but we are not considering that. We are taking infimum over all S here.
But that's not the remedy you are talking about.
No,
There is
that's
something
not the remedy I'm talking about.
Okay.
So there is actually some construction which will, if you apply to that QS, that will make it G continuous.
Okay.
And this turns out to be a pseudometric space. We have an example in the SL2R case that there are two norms which are not equal, but their distance is 0. So this is not a metric space, it's a pseudo distance. So once you have a distance on a set, now you want to, and you have maximal element and minimal element. Now you want to talk about how far they are apart. This is called the Sobolev gap. So this we term as the Sobolev gap. That is the distance between the minimal norm and the maximal norm. In other words, this is basically all those infimum of all those S for which the maximal norm is eventually swallowed by the minimal Sobolev set Sobolev norm of the minimal norm. So this we consider to be a interesting invariant, and our job is to, our purpose is to estimate this gap. So before going further into details, let me just mention few things about this, that this pseudometric and the Sobolev gap, they are independent of the choice of the maximal compact subgroup. So if you take any other subgroup, you can always conjugate, and then you can see that the equivalence of two norms doesn't really matter. Also, so to define this, we have used this definition of Sobolev norm using this K Laplacian. Now, if you use other Sobolev norm, what happens then? For example, if you use the standard Sobolev norm, you get something called something which we call the standard Sobolev gap, which is this. But this is actually a coarse invariant because now you are just taking minimum over only the integers. And also, since all these norms are sandwiching between each other, so we can show that this standard Sobolev gap and the usual Sobolev gap, they are actually equivalent. So that's why the family in this sense doesn't really matter what you are taking. So we are taking that family with respect to the K Laplacian because this is useful, or this is very helpful with the calculations. That's all. There is no other reason. Okay, now we have some properties for this Sobolev gap. If you the Sobolev gap of VW and Sobolev gap of the dual with this dual weight, they are same. In particular, if this V is self-dual, that is this, then the Sobolev gap will be this. And it respects the monotonicity of the weights. That is, if W1 is less than equals to W2, then the Sobolev gap is dominated by that Sobolev gap. Now we have something called an infimum construction, which will serve as the remedy for this G continuity of these Sobolev norms. So this says if you have a family of semi-norms on a vector space, we can define an infimum of that family of norms. This is simply by this. So this is basically if you have, if V are your function, then you decompose V, if you write down V on the supports, and then you apply Q alphas to those supports, corresponding Q alpha. And now if you have a norm P on V infinity, we define the infimum or the G invariant norm corresponding to this norm as the infimum of this family. WG inverse PG, the family is indexed by the group elements, which is basically the largest seminorm, which is dominated by all these seminorms WG inverse PG. And what about, when you do this infimum thing, it may it may happen that it turns out to be 0. But this can be prevented if you take if you have a norm which is below this norm. Then the infimum construction give you actually a norm which will not be a which will not be 0. That is, Q will be dominated by PG. And in addition, if there exists a G continuous norm which is above this norm P, then this G invariant construction belongs to this norm VW. And this implies that if you have a G continuous norm, then and you have a monotonous norm, for example, P is less than equals to PS with this Sobolev norm, then PSG, which is defined by taking this G invariant infimum construction, this turns out to be in the G continuous norm with this class W. Okay, and this has this nice stabilization property that there exists a S such that this PSG after that S turns out to be exactly coincide with the maximal class. So in particular, if P is a monotonous norm, for example, P is the unitary norm, then this says if you look at this Sobolev norm and take the G invariant thing, then after the Sobolev become the maximal norm. So if you want to visualize this, if you take a ascending chain, 0 less than equals to S1 less than equals to S2. Now you take the corresponding Sobolev norm. Since P is monotonous, you have P less than equals to PS1, PS2, blah, blah, blah. Then you get a ascending chain in the norm VW that with this G invariance. And this becomes stationary if you take the equivalence classes. That's we find it very interesting that if you with this infimum construction, any ascending chain, this kind of ascending chains become stationary after the Sobolev gap. Okay, now we talk about the G invariant norms and some results. So G invariant norms are the most interesting ones, which corresponds to the weight W1. And in this case, we denote the maximal and the minimal element as this. We just drop W from the notation. And we have our first theorem, which says that if V is a unitarizable and Q be a unitary norm, then in the pseudometric space, Q, the distance between the minimal norm and the unitary norm and the minimal norm and the maximal norm are same. That is, Q in some sense sits in the between the minimal and the maximal norm, and the Sobolev gap in this case is always dominated by 2 times this distance. Now we have some explicit result for SL2R, which is actually very surprising.
Pritam,
yeah.
Can you go back?
Yeah.
So this is one way, right? If V is unitarizable, then you have this distance to be equal.
Yes.
But does it characterize the unitary norms?
That we still don't know.
I mean, this is still an open problem, right? Which
yes, exactly.
I mean, so if you prove this, then it will be a progress.
Yes, there are a lot of open problems. I will just state in a few in a moment. Okay, now for SL2R, so all these things are for general G. G is real reductive. Now, if you specialize to the SL2R case, we have some concrete result. So you take G to be SL2R and V is a unitarizable, irreducible Harish-Chandra module. That is basically from the unitary dual, where you have this Q to be the equivalence class of the unitary norm. Then this distance is actually equals to half. And in particular, the Sobolev gap for all this all these irreducible Harish-Chandra module, which turns out to be uniformly 1. This, we find it very surprising that this SL2R, the Sobolev gaps are all same. Okay, so let me going too much into details. Without going too much into details, let me just give you the main idea of the proof. So you fix pi from the unitary dual, and look at the corresponding Harish-Chandra module, that is the k finite vectors. And recall that k in this case is SO2, so k hat is Z. And AS is the spectrum, k spectrum, that is all those n for which En occurs in the decomposition of V. For example, if pi is the unitary principal series, then AS is either odd integers or the even integers, depending on the parameter. Or if it is a discrete series, it is the natural numbers. Okay. Now we have an estimate for this k finite matrix coefficient. That is, it says if pi is any unitary irreducible representation, which is not the trivial one. So if you see, trivial one is actually not interesting, because on a finite dimensional space, all the norms are equivalent. So Sobolev gap is identically 0 for finite dimensional space. So that is not really interesting. And we have this estimate for this k finite matrix coefficient. It says that if you fix m from the spectrum, k spectrum, then the supremum of these matrix coefficients are bounded below and above by 1 plus root over 1 plus mod n. And this is true except for one representation in the principal series, which corresponds to the middle representation, that is the principal series representation with infinitesimal character is 0. And for that, you might have to add a log term, but that will not be creating any problem in our calculation anyway. And these estimates are uniform in k types. So this is something new. And with this, if you remember the definition of minimal norm and the maximal norm, with this you immediately have an estimate for the minimal norm. That is, minimal norm now behaves like 1 by root over 1 plus mod n. And since the dual is just the opposite, so dual will be behaving like 1 plus mod n. So behaving here, this notation means it is bounded below and above up to a constant. So for any S for which this Pmax dominated by the Sobolev norm of the minimal norm, so we must have this 1 plus mod n to the power half less than equals to 1 plus mod n to the power s minus half. So for those S for which this has to happen, S always must be bigger or equals to 1. This now, if you take the infimum, you always get the Sobolev gap to be bigger or equals to 1.
So now, here n is also from this spectral k pi, right? Not for all n, right? Or am I missing something? And this n in the theorem 5.
Yes, sorry.
N should also belong to.
Yeah.
Otherwise,
this is for all n. This is for all n from the spectrum.
Okay.
So this we have proved using the classification. That is, the unitary dual have a principal series, complementary series, and discrete series. So we have proved for separately. We have proved separately. So we need this spectrum. And for the other inequality, the main idea is this. We proved that the maximal norm is swallowed by the half plus epsiloneth Sobolev norm of the unitary norm. That will also tell us the distance between the maximal norm and the unitary norm is half. And since Sobolev gap is less than equals to 2 times that distance, so it is less than equals to 1. Now, how to prove this? For this, we'll prove that the unit ball satisfies the reverse inequality. That is, the unit ball corresponding to the maximal norm contains the unit ball corresponding to this Sobolev norm. And that is proved by proving that it is essentially, we have to prove that the maximal norm contains up to scale all sequences of this form, where ANs are a sequence from an L2. And now one can use some functional analysis and realize that the maximum ball corresponding to this maximal norm turns out to be the convex hull of this G orbit. If you fix some m, any m you can fix from the spectrum, then if you take the convex hull of the G orbit, it turns out to be the maximal norm. Then by convexity, you can take any complex Borel measure, then this thing will be inside Bmax because of the convexity. Now the main idea is to choose our gamma suitably so that this matrix coefficient, integration of this matrix coefficient asymptotically behaves like n to the power minus half plus epsilon. Now for this we have used some estimates of this matrix coefficient separately for each of the cases, that principal series, then discrete series and complementary series. And we have chosen our measure gamma suitably so that then we have to calculate and we have to estimate a lot of hypergeometric functions and gamma function to get this. I'm not going into the details because this is just too much technical. So that's the main idea of proving the Sobolev gap is 1 for SL2R. Now, let me talk about some few words about the geometry of this space norm V for SL2R. So first of all, what we have seen is that the unitary norm sits in the between that minimal norm and the maximal norm. Okay. Now, if V is a Harish-Chandra module of the unitary principal series and Q is the unitary norm, then we have this map I from minus half to half that takes every point to this norm VD by this prescription that is going to QSG. Remember, Q is the unitary norm, which is monotonous. So QSG is a G continuous norm. And this satisfies this. That is, the inverse map is actually continuous. And I also turns out to be injective. And we call this capital I to be the image of this iota inside this norms, inside this norm of V, which we call the central interval. In fact, if V is automorphic, then from the result of Bernstein and Reznikov, we have the the distance between the unitary norm and the automorphic norm is half. And also we have proved that the distance between the automorphic norm and the maximal norm is always bigger or equals to 1 by 6. We could not prove the exact value, but it is always bigger or equals to 1 by 6. And by our stabilization property in this picture, the maximal norm will always be equals to QSG when S crosses half. So this basically says this automorphic norm doesn't lie in that central interval. So automorphic norm is there somewhere outside the interval. Now we have this question of contractibility of these spaces. For example, if this map is continuous, then we can say that this is actually a contractible space. Also, one can ask about the different topological properties like connectivity or path connectivity. If also this map is continuous, then also we can say that this is path connected because you start with any norm. So you forget about this unitary norm. This map is defined for any norm for which PS is G continuous. Then those norm actually starting from that norm actually joins from that norm to the maximal norm. So if we can prove the continuity, then we can also talk about the path connectedness. So this continuity question is still open. Also, this if you remember the isometric norm PR. So what would be the distance of this PR from the unitary norm? For example, if PR is R is infinity, this PR actually captures the minimal norm, for which we know the distance already. So the general question would be, what would be the distance from this PR with the unitary norm, and what is the location of this LR norm, whether is it inside this central interval or not. So this will shed more lights on the Kuncz-Stein phenomena from a representation point of view, representation theoretic point of view. There are also a lot of other geometric questions regarding these sets. I'm not going into that. So let me finish with some. Let me just finish with few words about the general G. So we have this question is mine, that the uniform finiteness question given a real reductive group, whether this supremum of Sobolev gap is finite over the all family of Harish-Chandra module. F is a family of Harish-Chandra module. So we have positive answer to this question when F is a discrete series and the W is identically equals to 1. And F is a minimal principal series with the natural weights arises natural weights depending on the parameter, that is this. You take the induction from the minimal parabolic subgroup to G, call it sigma lambda, where lambda is any from the complexification of A star and sigma is any representation of M hat. Then we have this uniform finiteness of this minimal principal series. Here we don't need unitarity and all these things. This is uniform over all principal series representation. So now open question is whether at least it is uniformly finite over the at least for the irreducible representation, or if you look at the semi-simple Lie group, whether it is the Sobolev gap is uniformly finite over the Harish-Chandra's parabolic tower, or that is the representation corresponding to the cuspidal parabolic. Okay, so this is the reference for this talk, which will hopefully will appear soon in the archive. And that's all I have to say.
Okay, thank you, Pritam, for a very nice talk. Are there questions from the audience?
Yeah, I just wanted to verify one thing.
Yes.
So somewhere you said K smoothness and G smoothness are same. Can you go back to that slide?
Yes.
Just want to remind myself of the conditions.
So this is the slide.
So if you have a G continuous norm on, okay, I see. So if you have Banach globalization, K smoothness and G smoothness are same, is it?
Exactly.
That's what,
exactly.
Okay. Yeah. All right. Yeah. Thank you.
And Munada, for the Casselman subrepresentation theorem, you don't need irreducibility.
Okay, that's okay. Good to know. This I think is if you take W, okay, in certain cases, can you get some example of W where not B comma W is really phi empty set? Or
yeah, I think it is possible to construct such Ws. Because this W is actually connected with the growth of the representation. Right? If you take something below that.
And another thing is this if W is equal to 1, okay. So you mean to say that nor B comma W can be empty, right? For some W. Are you saying?
Sorry, I didn't get your question.
No, actually, it's okay. So you say that norm V comma W can be also empty for some W, right?
Norm V comma W.
So I was asking this question, can you give an example where this norm V comma W, okay, is an empty? So you said that it can be empty. Probably,
it is possible to construct such Ws, but we are actually not interested in those Ws for which this is empty. If this is empty, we have nothing to do.
Actually, if W is equal to 1, how do you get that norm of B comma W is always this P means isometric norm P of G dot B is equal to PB.
So this is our actually this is our convention basically. I'm not saying that less than equals to will imply equality. For norm for W equals to 1, we will all norm V will only denotes the isometric norms.
Okay. Norm of okay. And Tapendu, you want to ask some question?
You can change G to V to G inverse V, and you will get the other inequality, right? I thought W equal to 1 will imply it's an isometry.
Yeah. Actually, that implies. That's why I'm just saying that.
Oh, it will imply, right?
Yeah, it will actually imply. That's why I'm just calling this directly. That I'm just directly calling the G invariant norms.
Tapendu, ask.
Yeah, so thank you, Pritam, first for this long but nice talk.
Thanks for tolerating.
But yeah, it's heavy, but I think you explained very well. So could you go to this Casselman-Wallach theorem?
Yes.
Yeah, so here you say, I don't know these things very much. So when you say for pair of G continuous norm, there exists a K belongs to N. So do you have any estimate for such K, or this is coming from abstract theory? Like
So our estimate for the Sobolev gap, uniform estimate of the Sobolev gap is going to give the quantitative estimate for this K.
Okay, so there exists some estimate. It's not that coming from
Casselman-Wallach only proved the existence of such K.
Okay.
Now for a quantitative version, we are offering this estimate for this Sobolev gap.
So from your theory, you get an estimate on K, you're saying?
Yes, yes. In terms of Sobolev gap.
Okay, that's nice. And in your theorem 3, so I'm not sure about this question, but could you go to that? Yeah, so here you've taken Q be an unitary norm, and
yes.
then okay, Q be an unitary norm, and norm B D, and D is the what is D again? I'm sorry, this norm
D
B
is the
D
distance.
Distance.
Distance defined on that pseudo distance.
And this is using the for particular P, right? D is defined, if I remember correctly.
No. D is not for particular P.
Okay.
D is this.
No,
DPQ is this.
Yeah, so my question is, instead of taking W equal to 1, if you take W equal to WP for G continuous norm, do you have any say on anything on this for this kind of norm V WP?
And this is going to be a pseudometric space. That's all we can say now.
Okay, but
you
cannot say
if you start with any G continuous norm, you have this WP.
Yes, but you cannot say any analog of theorem 3 for W equal to WP.
Because if it is unitarizable, then we can say, of course.
Okay.
If it is not unitarizable, then we don't know about this theorem.
Okay. Thanks.
So what did you explain this? Can you explain this term minimum globalization by Schmidt, which was used? So what is the meaning? It is called minimal.
Okay, so roughly speaking, minimal means just if you take any other globalization, it will sit below that. So for example, if you take this example, so here all these things are globalizations. Okay. And these analytic functions will be below everyone. I have not written analytic functions here, but still it's there.
So here in this setup, what is the minimal globalization? Analytic functions.
Analytic functions. Yes, analytic functions. It is true for any Harish-Chandra module. Actually, if you start with any Harish-Chandra module, the analytic vector, the minimal globalization corresponds to the analytic vector.
Okay. And there's another small question. Probably it is the thing. Something is LP tempered distribution. If matrix coefficient belongs to LRG for R greater than 2, okay, all matrix coefficient.
Yes.
Can we conclude that if one non-zero matrix coefficient belongs to really LRG for R greater than G, then all the matrix coefficient will really be in LRG for R greater than 2? Like the discrete series case.
I think you can look at this recent paper of 2 Canadians. It's in JFA. They considered this problem. They approached via sister algebra.
Okay.
I think the result was if there exists a diagonal matrix coefficient corresponding to a cyclic vector, which is in LP. P is bigger than 2, let's say. Because P less than 2, or P is 2, then there is nothing to prove. It is already there. If P is bigger than 2, if there is a diagonal matrix coefficient corresponding to a cyclic vector, then all the matrix coefficient will be in LP plus epsilon. That's the result.
Oh,
Not really P. It will be in LP plus epsilon.
P plus epsilon. Okay.
Yes.
Okay. So are there any other questions from the audience? Okay. If there are no more questions, let us thank the speaker for a wonderful talk. Okay. Let us unmute and thank the speaker.